Good day everyone, I am Ana Maria De Leon from BSIT 2A WAMAD and we're going to discuss 10 equations from probabilistic theory.
The first equation is three disjoint events. Given A, B, and C. So the probability of A union B union C is equal to the probability of A plus B, probability of B plus the probability of C. So here are our sample space, and inside there are three disjoint subsets. Subset A, B, and C. So the probability of A union B union C is equal to the probability of event A and B. So the probability of union B plus the probability of union C. For instance, A is equal to 1, 2, and 3, and B is equal to 4, 5, and 6, and C is equal to 7, 8, and 9. So the probability of A union B union C is equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we can conclude that the probability of A union B union C is the sum of the probability of A plus the probability of B plus the probability of C. So we prove that the probability of A, B, and C is the sum of the probability of A, B, and C. Our second equation is if A is the subset of B, then the probability of A is less than or equal to the probability of B. So here is the sample space, and inside is the subset A and the subset B. So B is equal to A union of B intersection of event that does not belong to A but belongs to B. So probability B is equal to probability of A plus the probability of B intersection A is greater than or equal to the probability of A. So we prove that if A intersection is the subset of B, then probability A is less than or equal to the probability of B. Our third equation is probability A union B is equal to probability A plus probability B minus the intersection of both A and B. Probability of A intersection B. So here are the sample space, and inside is A and B. So first we're going to get the probability of A occur. So A happened here. So A intersection of B complement, event that belongs to A but doesn't belong to B. And when both A and B occur, then here, so B in A intersection B. And if B occur, this is happened here, you can say that probability B intersection of A complement. So probability A union B is equal to probability A plus probability B minus the intersection of A and B. You can cancel B here, and here we're left with A, B, and C. So we prove that probability A union B is equal to the probability of A plus B minus the probability of intersection of A and B. Our fourth equation is probability of A union B union C is equal to the probability of A plus the probability of A complement intersection B plus the probability of A complement plus intersection of B complement intersection of. So here are the sample space, and inside are the subsets A, B, and C. So probability of A union B union C is equal to the probability of A probability of A, event that happens on A, plus the probability of B plus the probability of B intersection of event that happens to B but will not occur on A. So A complement plus the probability of C intersection of event that happened to C but does not occur on A. B complement intersection of event that occur on C but does not occur on B. So B complement. So here we prove that A union B union C is equal to the probability of A plus A complement intersection B plus the probability of A complement intersection of B complement and intersection of C complement. This equation is probability Z is equal to 2 So we have two rows of four-sided die. So the probability of here are the sample space. And there are 16 possible outcomes. And Z means the minimum is equal to 2. Meaning, the first row will will result into 2. And the second row will result to 2 or greater than 2. So in this case, there are 5 possible outcomes. So the probability of Z is equal to 2 is equal to 5 times 1 event occur over the sample space. So 5 is the sum of the probability of Z is equal to 2 and 16 is the sample space. It's conditional probability, and the formula is the probability of A given B is equal to the probability of A intersection of B divided by the probability of B. For example, two rows of four-sided die, and let B the minimum of X and Y is equal to 2, and the maximum is equal to 3 given that the minimum is 2. So our sample space have 16 possible outcomes. So first we're going to get the minimum of 2. The minimum of 2 or greater than 2. So for instance, the first row is 2 and is equal to 2. The second row is equal to 3 and the minimum is 2. Fourth row is equal to 4. The third row should say is equal to 4 and the minimum is 2, and the second row is 3 over 2 and forever 2, and then the maximum is 3 or less than 3. So here and here. So according to the formula, the probability of maximum of 3 given that the minimum is 2 is equal to the probability of the intersection of both maximum of 3 and the minimum of 2. Divided by the probability of the minimum of 2. The probability of B is equal to, first we're going to get the intersection of these events
So there are, in this sample space, there are two intersections. So 2 over 16, and the minimum of 2 have 5 um, 5 possible outcomes. So 5 over 16. So to simplify it, we get 2 over 5. Our seventh equation is detection of an object in the sky by a radar. We have two events. Event A represents airplane is flying above, and event B something represents something registered on the radar. In this equation, we can represent it by a tree diagram, which we have two probabilities. Probabilities A occur and probability A does not occur. In this probability A occur, we have two possible outcomes. The probability A and B occur, and the probability A and B does not occur. In this probability, the probability of A does not occur, we have two possible outcomes. The probability A does not occur and probability B occur. And the probability A does not occur and probability B does not occur. And the formula in this equation is the probability of A intersection B is equal to the probability of A times the probability of B given A. To compute this, we're just going to focus in this part, the probability of A and B occur. So to compute that, given the formula, the probability A here is equal to 0.5 times the probability of B, given that the probability of A is equal to 0.99. So the probability of A intersection B is equal to 0.049. So that's the computation of this equation, the detection of an object in the sky by a radar in this probability A, in which probability A occur and probability B occur. In our eighth equation, we're going to focus on multiplication rule, which applies when you want to find out the chances of the intersection of two events. That is, the chances of both events happen. The formula is the probability of A intersection of B is equal to the probability of A times the probability of B given A. So in this example, you want to find out the probability of the first drawing of a green marble and then a blue marble in a bag of marbles. So we have 12 total marbles, which is 3 greens, 4 blue, and 5 red. So given the formula, we're going to find out the probability of the first drawing of green marble and a blue marble. So the probability of green marble intersection of a blue marble is equal to the probability of green times the probability of blue given green. So the probability of green marble is equal to 3 over 12, or to simplify that, we're going to get a 1 over 4, or 1/4, or 1/4. So the blue probability of blue marble is equal to 4 over 11, because we already drew the one marble, so we only left a 12. So the probability of green intersection of blue is equal to 1/4 times the probability of blue given green is equal to 4/11. We're going to cancel for here, and we'll have 1 over 11. So the probability of the first drawing of green marble and then the blue marble of a bag of marbles is equal to 1 over 11. So in our ninth equation, we're going to focus on the total probability theorem, which the formula is the probability of B is equal to the probability of B is equal to the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. So here we have an example. A tennis player wins 60% of her match when she scores the first point in the first game. She wins 10% only of the match when her opponent scores the first point. If she scores the first point 30% of the time, what factor of matches that she wins? So here we have the value of first we're going to let SF represents the first score, or score first, and W represents win. So here we have the value of the probability of win given she scored first is equal to 0.6 or 60%, and the probability of win given that she does not score first is equal to 10% or 0.10, and SF, which represents that she scored first, is equal to 0.30. Now we're going to find the probability of win. So here we have the formula, and we're going to write the probability of win is equal to the probability of she win first over given that she scored first times the probability of score first plus the probability of the probability of win given that she does not score first times the probability of she does not score first. Here, we're going to get the value of this by subtracting the probability of she win first, the probability of you win first minus 1. So we get 0. Going to write it here. Probability of she does not score first is equal to 0.7. So we're going to change that into here its values. So here we get 0.60 times 0.30 plus 0.10 times 0.7, and we get the probability of win is equal to 0.25. And our last equation, we're going to focus on Mike's rule. So here I have a example. You're planning on a picnic. You're trying to decide whether to postpone due to rain. The chance of rain on any day is 15%. The morning of the picnic is cloudy. The probability of it being cloudy is 25%. And on the days where it rains, it's cloudy in the morning 80% of the time. So here we have the formula of the probability. Here we have the formula of the probability of B. The probability of A, I should say, given B is equal to the probability of B given A times the probability of A divided by the probability of B. Here in the examples, we have the probability of rain is equal to 0.15. The probability of rain cloudy is equal to 25% or 0.25, and the probability of cloudy given rain is equal to 0.80. So we're going to get the probability of rain given cloudy. So the probability of rain given cloudy is equal to the probability of cloudy. The probability of cloud, going to write, C represents the cloud, cloudy, given rain, R represents the rain, times the probability of rain. Probability of rain divided by the probability of cloudy. Let's change the values. So the probability of cloudy given rain is equal to 0.80 times the probability of rain is equal to 0.15 divided by the probability of cloudy is equal to 0.25. So the probability of rain given cloudy, the probability of rain given cloudy is 0.48. That concludes our discussion of the 10 probabilistic theories. That is all. Thank you.